a hectare approximately. You've got I can't do the maths now, 1,000, over 1,000 million tonnes of potential usable biomass that's currently a problem. You're not taking away material that's usable in a current format. You put it into context, what's the global pellet market? 55 million tonnes. Counteract that with how much coal is currently sold, 7,000 tonnes per annum. So the challenge presented to us and why we were approached was, can we stimulate the harvesting of that bush? Because at the moment it's a cost, and what we wanted to do was create value from it. And that's where this project has taken us forward. So looking at it, the situation now, Southern Africa, coal is the primary energy source, is an unreliable status, it's not very environmentally friendly, there's a lot of rural unemployment, there's social inequality, you have the encroachment problem, you have the invasion problem, and nothing's actually dealing with that. So what do we want to do? We want to turn a problem into an opportunity. Now that sounds a bit twee, like out of a business school, but it's a real, genuine thing. We want to turn the problem of the unwanted biomass, the encroacher bush, the invasives, into a clean, secure fuel that can create jobs and address poverty. And we want to do it in a way that benefits the society as a whole. So how are we going to do that? We want to take the original project forward. We've built that unit. It's a demonstration unit. We're looking at it not just to prove it on a techno-economic basis. We're looking at it full sustainability. Do we leave the land in a better place than it was before? Do we create social benefits? Can we do a good thing environmentally? So very much a holistic reach in this. If anyone's been involved in an EU project, you have your work packages, all very great. And I could go into the details on that, but I think we've all got a limited lifespan. Core things of what we are doing now, other than proving it on all the various aspects, we are currently turning our prototype design into an industrial scale replication. We're talking about taking a system that's currently 250 kilos an hour, which gives an output nearly 4 tons a day, into a system that can operate 2 tons an hour as a first commercial deployment. We're also looking at the full business case so that we can roll it out, we can secure investment, we can take it forward. And this is what it looks like. Nice little demonstration at the Cheetah Conservation Fund site in Namibia. Wonderful place to visit. Wonderful to see the cheetahs doing their morning run, hurtling around the park. Really lovely place, but also you see firsthand the level of encroachment because you're in the middle of that encroachment area. So where have we got to? We've built the unit. We're demonstrating the unit, we're optimizing it. We're producing, within the next 6 months, we'll have produced over 500 tons of material. That will be demonstrated and validated in communities in South Africa, Botswana, and Namibia. It also will be validated with industrial units, a cement works, a copper mill, and factories, particularly in southern South Africa, who are using coal and validating it. We have a good relationship with a major manufacturer. We're looking to progress what we're doing into commercial scale rollout. So what's next? Continue producing, get our 500 tons an hour. Sorry, that would be nice. 500 tons produced to test. Prove that the economics stack up. Lots of people talk about, well, I've got this great plan, but actually produce a business case. One of our partners is owned by a green investment fund that's pulled down $60 million US dollars, not Namibian dollars, I should add, in investment in new capital, green capital projects over the past 4 years. We're developing plans for post-project scale-up. So, as with anything in an EU project, we're looking at quite a few partners. 15 partners, 2 continents, 8 countries, researchers, academia, industry and entrepreneurs. We're all doing fine and everyone's happy with each other all the time. Well, not really, but we're working and challenging and addressing the things. It's a complex piece of work and I think we're getting there. Thank you. And if you want any more questions, please visit us today or tomorrow at our stand. Thank you.
Thank you for this very good presentation. Is there any quick question, or should we leave that for a discussion at the end? I can't see any. So, Gang, if you will to continue.
Good afternoon. My name is Gang Xian. I'm CTO and the co-founder of WAIES Environmental Solutions. Today, the topic is ensuring a sustainable future by replacing fossil carbons with biocarbon. Steel industry is one of the most difficult industry for decarbonization. Carbon, especially fossil carbons, are used as a reducing agent in the steel-making process. In 2021, over 1 billion tons of coal has been consumed in the steel-making process. Free allowance in the emission trading system are phasing out for the steel industry. And the carbon border adjustment mechanism has just been implemented since October last year. Those will drive fossil carbon cost to increase dramatically. Hydrogen can be used to replace coal and coke for steel making. However, converting a conventional steel mill to a hydrogen-based mill will cost 3 to 7 billion euro. So this is happening, but it will take decades. The urgency is already here. So the industry needs a more cost-efficient solution right now. Our solution is based on biocarbon. Biocarbon is made of forest residue. Forest residue is one of the most abundant carbon sources on Earth. It has not been well utilized. Using pyrolysis technology, we can convert forest residue to biocarbon and then use our formula to produce biocarbon pellets. Those pellets share many similarities with fossil carbons. And then the steel makers can use those fossil carbon, can use the biocarbon to replace fossil carbon directly in the existing facility without involving too much infrastructure changes. 1 ton of biocarbon can replace up to 1.3 ton of fossil carbon and reduce 3.3 ton of CO2 emission. First, let's see how fossil carbon are used in the steel-making process. In blast furnace, which accounts for nearly 80% of iron production globally, use PCI coal and charged coke as reductants. Each year, there are over 900 million of fossil carbon used in blast furnace. For each ton of steel made in blast furnace, average CO2 emission is 2.5 tons. There's another mainstream technology called electric arc furnace, which accounts for 22% of the total steel production globally and 40% in Europe. Since electric arc furnace mainly uses scraps as a feedstock, it has a lower CO2 emission than 1 ton per ton steel. But in total, it still requires fossil carbon 6 million tons per year in the electric arc furnaces. If we look at the entire metallurgical industry, steel accounts for 95% of the market size. The other 5% is for ferroalloy production. And many ferroalloy production processes cannot use hydrogen to replace fossil carbon due to thermodynamic reasons. They have to use a solid carbon in process such as ferrosilicon, ferromanganese, ferrochromium, and aluminum production processes. And coke and coal use reductant. Calcined petroleum coke also used as a packing material in aluminum anode packing material, packing furnace. So in total, the ferroalloy market size is 80 million tons per year. Based on what metallurgical industry needs, we have developed two different products. One is injection biocarbon, mainly aiming for steel industry for PCI coal replacement. And the second one is a charged biocarbon for charged coal and coke replacement in both steel and ferroalloy industries. For black furnace, we can use injection biocarbon and charged biocarbon to replace a small part of fossil carbon. But in electric arc furnace, we can use injection biocarbon and the charged biocarbon to replace 100% of fossil carbon. For ferroalloy industry, electric submerged arc furnace, we can use charged biocarbon to replace fossil carbon and also use charged biocarbon to replace calcined petroleum coke in aluminum anode baking furnace. There's one bonus. If we use charged biocarbon as a carburizer in electric arc furnace, then 70 to 90% of carbon will stay in the steel for many, many years, which make it a carbon storage technology. Biocarbon will be more competitive than fossil carbon in the future, in the near future. For steel makers, they will benefit first without using fossil carbon, which is typically imported from another continent. Second, they can avoid paying CO2 tax. Third, they can gain premium price for the green steel they make with biocarbon. CarbonWorks is our trademark for biocarbon production facility in Norway. In CarbonWorks, we convert forest residue to biocarbon via pyrolysis technology. And syngas is burned and the heat is recovered as steam and hot water. So we can supply excess energy to a neighbor factory or a district heating network as a second revenue. But the location of CarbonWorks, for current CarbonWorks, has to be considered next to a factory or industry park or urban area due to the heat sales requirement. So we use pyrolysis technology to balance fixed carbon and the volatile carbon content in biocarbon product. The technology we use is internal heated slow pyrolysis. It can be operated at quite high temperature continuously for a long time. For certain metallurgical sectors, actual low volatile matter is desired. Then quite high temperature operation need to be maintained for a long time. And our technology can also treat different type of materials such as sawdust, wood chips, bark, and wood trunks. And is highly scalable. One full-scale unit can have a big amount of biocarbon production. Last week, we carried out a trial with our pilot reactor. We produced 5-ton biocarbon with 3 different types of feedstock. And 4 tons of the biocarbon was produced from Norwegian spruce sawdust. So pyrolysis is used for balance fixed carbon and volatile carbon. For other properties, such as compression strength, thermal strength, durability, reactivity in furnace, resistance to moisture, and bulk density, we use formulation technology to do the control. The formulation technology combines biocarbon grinding, binder mixing, pelletizing, and hardening steps. We have developed unique binder formula for different product series for different customers. We can also feed different type of carbonized material, such as biochar, biocarbon, and charcoal. Each unit is designed at quite high capacity and standardized for 10,000 ton output per year. And our first full-scale demo plant will be commissioned by the end of 2024. Have you heard how beautiful biocarbon sounds like? There's a small video. So this is a trial we carried out in 2023 with a full-scale pelletizer. Thank you. Sustainability is very important for the steel industry. It's also key for biocarbon production. We use forest residue only from certified forest material, such as PEFC and FSC. Feedstock security is very important. And we are competing with those companies who burn biomass directly for energy purposes. So the good thing is the EU has launched the cascade principle, which prioritize material recycling over bioenergy purposes. After Renewable Energy Directive 3 announced, EU countries will put a new policy to favor material recovering over burning biomass directly. There has been a lot of sawmill byproducts sent to combustion plant for energy purpose. And this involves lots of truck traffic in sawmills and lots of sawmill byproducts value lost during transportation. Our approach is to set up a biocarbon production facility in or next to the sawmills. In this way, we can realize material recycling and reduce truck traffic in sawmill by 90%, and also send thermal energy to sawmill for their product drying. Then they can avoid investment on new boilers. And we get the biocarbon and send to local steel makers for fossil carbon replacement. In this way, we empower the entire value chain. We see securing forest residue is very important for our success. So we develop ultimate value creation products from sawmill byproduct, for forest residue. On one hand, we upgrade the biocarbon to hard carbon and use hard carbon in sodium-ion battery and the lithium-ion battery as anode material. On the other hand, we upgrade syngas with a fermentation process to protein. And this protein product can be used as a fish feed ingredient. From syngas to protein, so-called synoprotein process, is a CCU process with a negative carbon footprint. Together with a top university and research institute in Nordic countries, we have secured €6 million to develop a new product. This diagram illustrates how future carbon works look like. Forest residue will first convert it to biocarbon and then upgraded to hard carbon. Part of the syngas will be combusted and supply thermal energy inside the plant. The rest of syngas will be converted to a protein product via fermentation. In this way, we can have a good energy balance inside the plant, and we can locate our future carbon works to forest residue sources in a remote place if necessary, because we don't have to sell energy to a neighbor factory anymore, and then we only transport solid, easy to handle product to our customer. A little bit about our company. Why Environmental Solution is Norwegian bio-based carbon material technology company, founded in 2017. Now we have a team of 9 scientists, engineers, and business people. Our headquarters is in Tønsberg, Norway, and a fully owned branch office in Suzhou, China. We focus on forest residue to biocarbon conversion. Thank you very much for your attention. Thank you.
Thank you, Gang, for this good presentation. Is there any question? Not for the moment. So, Marko, to you.
Hello. My name is Marko, as earlier mentioned, and I'm representing company CORTUS Energy. Today I'll talk about proven bioenergy solutions by modular wood roll technology that we are having. First, briefly, an introduction of CORTUS Energy and the wood roll technology, the Höganäs, which is a metal powder producer project, and the modularity of the technology that we are having. So, to start with, I have been part of the company since 2011. I can't say that we are a startup company, as we have existed since 2006 nowadays. We are having a 0.5 megawatt pilot plant. We are having a demonstrational plant down in southern Sweden. We have, over the years, been conducting several engineering studies for customers, mainly industrial customers. The project pipeline at the moment involves basically interest from all over the world. Though our main focus is national, Nordic, and European countries. We are still a fairly small company, 33 employees, where majority is located in our demonstrational plant down in southern Sweden. The technology itself, to start with, it is three-step technology where we take biomass, bio-waste. It can come from wood, or it can be a crop, or it can be an industrial sludge, industrial waste. We dry it to between 5 and 10% humidity. Then we are taking the dry fuel and we are pyrolyzing it, slow pyrolysis at around 400 degrees. And what we then do is that we grind the char that we have produced and we gasify the fine grounded char with the steam. To provide the gasifier with heat that operates at 1100 degrees, it is indirectly heated radiant tubes that are heating the gasification. As it is char steam gasification, it is strongly endothermal, which makes that majority of the energy from the pyrolyzer is needed in the gasification process. What we then do is that we take back the remaining flue gas energy to heat the pyrolysis and the drying process. We then cool down the syngas produced, and by cooling it down from 1100 degrees, we are producing our own steam. The energy balance is a bit dependent on the humidity of the fuel. That is the main factor. But for around 30% humidity of the incoming fuel, we have about 80% energy yield, syngas in comparison to the raw biomass. We are having patents, different patent families in different parts of the world. Little bit the story of where it all started many, many years ago. We see now, when I retroactively look upon it, we were far too early with our technology in comparison to what market wanted at that point. There was never a chance at 2012 to compete with the fossil fuels towards the industrial segment. But anyhow, we were having our pilot already at that point. So through several steps, we have went from gram level together with university to go up to 150 kilowatt scale. At that point, it was basically grinding made with type of grinders that you grind food with at home. Later on, we went to 0.5 megawatt pilot unit that we built on different steps until it was fully integrated around 2016. And now we are having a demonstrational unit down in southern Sweden, as I mentioned, where we have about 20 persons employed. The best thing with our technology, I would say, when we look upon it, is when we scale up and when we use it for catalytic applications. As we are only using steam as oxidizing agent, there are no traces of nitrogen in our gas. And as we are also operating gasification at so high temperature, there is no need of cleaning downstream the gasification process. The biomass gasification, it is definitely key of renewable future, and now perhaps also there is a timing in the market that is to our benefit. As you heard here before, there is a strong need, and the time is very close to when it is not just good to reduce your emissions, it is necessity for many industrial sectors. A little bit about the Höganäs project. It is a 6 megawatt plant for syngas delivery. We are replacing natural gas. Höganäs AB is the customer. It is a pipe replacing the natural gas that they are using today. And we have received grants for building this plant from different project partners. The organization on site, 5-shift, 24/7 operation. We have site engineering team, site maintenance team. Also, for analysis, there is a support from our main office in Stockholm, where we have the process engineering team. And of course, the key is also our customer. What have we then done during 2023? We are still not in 11 months per year operation, which is the final goal. We are today operating daytime. We are going over to 24/7 operation. The reason is that we have needed to educate 5-shift from the customer as well to operate the furnace with syngas, as they normally only operate natural gas. What we also have achieved during the last year is biochar. Biochar is something that really didn't exist when this plant was built. Now I'm talking about biochar for ground purposes, not for coking purposes that we also heard here before. But over the time, we realized that, but wait, we do have a capacity. We are already producing char as a part of our process, and all of a sudden, a market has come up that really didn't exist. So we went through certification. We also, when we see issues in the plant, in the gasification part, we can continue on to produce biochar. So during the last year, when we were standstill during the summer, we produced around 150 ton of biochar. So this is really a possible product out. Some other historical achievements. We have historically also produced biocoke for metallurgical applications. Then, as you heard before, we need to heat treat it to higher temperatures to reduce the volatiles. We also need to compress the biochar as it has too low density. This part has not been done by us, but by steel partners before testing it. What we also have done and are doing still, it is that, well, okay, if biochar is a possible product out, all of a sudden we have quite a lot of surplus of energy if the gasification is not in operation. So what more value than district heating with possible electricity can be made by the gas and the energy we have there. So we are performing some tests with by hydrolyzing the pyrolysis gas to see can we get an oil product, as the pyrolysis gas in room temperature that we have from our pyrolyzer basically is 50% gas, 50% oil, water, tar mixture, if you would. So here we are having national funded projects to do more evaluations on possibility of replacing fossil oil. We have also, with the syngas composition, you saw, upgraded it historically and converted it to biomethane through catalytic reactors and upgraded it and compressed it to fuel one of our biogas cars. Little bit about the modularity and where do we see ourselves. Well, we see ourselves as the stem, and this is our core technology. So we can have the biochar is not even in one of these squares for as fertilizing agent. We have the possibility of increasing the temperature more for usage in steel industry. There is a possibility of utilizing in the future the pyrolysis gas, but our main target where we are right now, it is the syngas itself. The syngas itself down in Höganäs is used to replace fossil gas in process industry, but over time the most benefits are seen of converting it catalytically to more valuable fuels, such as alcohols or liquid fuels or even as chemicals. A bit shortly about how is it that we see our projects. It is, of course, every time dependent on the type of fuel and the case the customer has. The cost of the fuel is the main cost by far of the OPEX of this type of plant. So pre-drying may be necessary. For that, it is very beneficial if there is surplus heat, if we are located at an industrial customer. Drying can be scaled up conventionally up to 50 megawatt units. We spoke about 6 megawatt that we have as demonstration. The pyrolysis, which is the heart, we see already that one at 25 megawatt unit. And really the bottleneck as of today in our technology development, it is the gasification units. And it is really the heating of gasifier, the tube heating of gasifier. We are today 6 megawatt level. We are having 20 megawatt under development for scale up. And this is basically, we need the scale if we are about to use the syngas for catalytic processing as downcoming proven processes such as Fischer-Tropsch are very costly. So they have hard today to compete on 6 megawatt scale. Yes, little bit about the type of the plant we can have or are having. I wouldn't have considered this 5 years ago as an option, but what we have seen over time with biochar that has come more with some industrial applications where there is not a need of this clean syngas that we are having, it may be enough to reduce the capex by having a much more simple plant. And then, of course, there is the possibility of having the full application with where we are producing our syngas for different type of processes. That was all that I had. Thanks a lot.
Thank you, Marko, for this very clear presentation. It seems that there are some questions now. Any question?
Yeah, thank you very much for the very nice presentations. I have a question for Mr. Gangtin. You talked about the fact that it's possible to replace up to 1.3 tons of fossil coal by biocarbon in the steel industry. Can you explain a bit more how it is possible?
This is working? Yes. Steel industry look at biochar or biocarbon as reducing agent, and it's typically the fixed carbon content counts the most. So if we can generate a product has a high fixed carbon content and replace either coal or coke with a relatively low fixed carbon content, then we can use 1 ton to replace 1.3 ton.
Okay, that's clear. Thank you.
Any other question, comment? Maybe you wanted to put a general perspective of these three technologies, because we are in a new ground of defossilization here.
Okay. Can't quite remember what I said earlier about bringing them together. But, however, I think all three projects and initiatives that we've been talking about, we're all at that level where we're transcending the valley of death. We're getting closer to market. All the work we've been talking about are applying technologies to real-world issues, real-world problems in a green and sustainable approach. The approach and what we're doing is different. We're looking at different temperature ranges. We're looking at different markets. We're looking at different options. But I think there is a strong commonality between the three projects, and it's very interesting listening to the two other talks today. Thank you.
Thank you. Hugo? Do you want to comment on anything?
No, we can all go home. Right.
Okay. Is there any comment, question in the audience? Or should we leave it as it is now and wish you all a very good evening and very good continuation of the show? Oh.
Yeah, a question for CORTUS. How is it possible that you have so much hydrogen in your syngas? Because we don't see that a lot. I think it was 59%.
Yeah, it is. It has nothing to do with the biomass, of course. So much hydrogen there is not there. But we are only putting steam as oxidizing agent in the gasifier. So when steam is splitted, we get hydrogen and CO only as... so it comes from the steam totally. And we have done several tests. This is a public report as well, when we have both used fiber sludges with 8-10% ash, but also crops, but also wood residues. And the hydrogen content is rather a matter of steam to char ratio in to the gasifier. The more steam in relation to char we put in, the more hydrogen we get. Hydrogen and CO2 will be higher. That is rather the difference in syngas than if it is a fiber sludge or a wood chip. So, and this is, if you're looking upon this is a public report that we have presented. So it is really.
Okay, thank you.
It comes from water.
Okay, so only steam, no oxygen at all, not a mix of. Okay.
No oxygen, no air. So.
Which temperature?
1,100 degrees.
Okay. Thank you.
I have a follow-up question, Marko. So there's no nitrogen in the syngas either?
No, there is no nitrogen in the syngas either. In the case of Höganäs, where we are replacing natural gas, there we are having backblowing of bag filters with nitrogen, as that is the most cheap inert. So because of that, we are having 0.2% because of the backblowing of filters. But in a catalytic approach, it would be carbon dioxide that would backblow the bag filters, and then it would be no nitrogen.
Thank you. Any other question? Well, I thank you, our three presenters, for the excellent presentation. And it's time to wrap up and see you tomorrow for the continuation of the presentations. Thank you.
Thank you.
It's always hard to ask.